basically, the start is going to just give you an overview of what tablet PC is and its potential. I'm going to show you a number of applications. Unfortunately, some of the applications I'm going to show are not the ones that we developed. We have developed something very similar to this, but some of them that I'm going to show are professional versions of them. So Microsoft, when it does the same thing, it produces a fancier looking front end, and so you will see some demos, but I'll also describe along the way exactly the type of work that we will be doing, but at the same time I'm also going to get you all interested in problems related to this field, because there are lots of interesting things that can be done in this area. So the overall outline of the talk is as follows. I'll first start by talking about the pen-based, the so-called tablet PC. In fact, what I'm using today is a tablet PC. So you'll see my presentation itself as an application of this technology. And I'll talk about various potential applications. And I'll also describe some of the completed projects. I gave a list of several master's projects, and I'm going to briefly touch upon those. And then I'll spend a little bit of time talking about various tools and techniques needed to implement some of these projects. And then I'll conclude with some potential future projects. Standard interfaces to your computer are keyboard and mouse. And the new interfaces keep coming up. Some of the more recent ones are voice interface. So there are, now this has almost become a standard choice in desktop computers. You can interface through voice, and you can give a command orally and get the operating system to start functioning. And another option is to use a pen. So, like there. Okay, so just using a pen, you can write on the screen. And so the basic attributes for a pen are its position. Then you place the pen tip, the XY coordinates can register. And you can choose the color. And you can choose thickness option, you can use pressure. All this information gets recorded and can be used to create various types of applications. The brief history behind the tablet PC, it looks like interest in this notion predates modern electronic computer. In early 20th century, when we didn't even have a fully working computer, people had already thought about creating handwritten input through an electrical signal using a tablet. And one of the pioneering work in this direction is by an essay called As We May Think by Bush. And this article has now become one of the most widely cited articles, because it really became the inspiration for the so-called hypertext technology. So basically, he was trying to suggest that you can try to read in a navigational mode by using some kind of a link that connects documents, different documents. So this became the basis for the so-called HTTP protocol and so on. Another interesting thing about Bush is that he was the thesis advisor of the famous Shannon. All electrical engineers don't need an introduction to Shannon. So he was the advisor of Shannon at MIT. And this article is now one of the most widely cited ones. And moving further along, a very important work came out of the Palo Alto Research Center. A person named Alan Key, who got his PhD at the University of Utah, under another person named Sutherland, who is also very well known for his attempt to provide friendly user interface to computers. So some of the early work was done by Sutherland, who, in fact, he's one of the pioneers in the concept of computer graphics. And so Alan Kay, when he came to Xerox Palo Alto, proposed the concept of a notebook using pen input. Although that particular proposal that he put forth never materialized, Kay's idea became the basis for Apple computer. So the first generation, the concept of a mouse and a mouse input to a computer was inspired by Kay's work. And Kay also created a language specifically for this purpose called Smalltalk. And again, in that way, he envisioned the so-called object-oriented programming. So these are some of the pioneering efforts. I'm not giving a complete history at this point because from this point onwards, all the developments are technological in nature. So the concept was there, but we need to actually realize it, so which means that you need to have better sensors and more sophisticated, faster receivers for the pen input and so on. So the successive development along these lines in 80s and 90s finally resulted in commercial production of this product in 2001, when actually Bill Gates gave a talk with tablet PC for his presentation that really became the point at which this became a commercial product. So what can we do with this new interface? So the next 15 to 20 minutes, that's what I'm going to focus on, and give a number of examples of the ways in which you can use this medium in a number of different settings. So some of the most obvious things you can do are you can take notes and draw sketches, and you can combine them easily with the digital documents, just like what I'm doing. So for example, I can just draw something like this and just save this whole file, and I can post it, share it, and so on. Right? So it's very easy to combine the benefits that come with input through keyboard and mouse, and the benefits that come with freestyle writing with a pen. Right? So that's the obvious way in which we can use this tool. And clearly you can therefore use this idea in classrooms. In fact, a lot of research in tablet PC centers around the idea of using this technology to enhance education. There are lots of conferences that are taking place at various levels. In fact, there are many high schools in which people have acquired tablet PCs, and both the instructors as well as teachers, as well as students, use this and then they exchange material and so on. So ranging from school level all the way to graduate school level, at every level people are trying to improve the ability to teach and to impart education in a more effective way using this technology. Another area could be artwork. In fact, I want to show you in a few minutes a very simple way in which you can use this tool to create your own art form. It takes less than 30 seconds to do some sketch. But what is more interesting is that you can use this idea to actually develop computers to create art form that mimic human artists and so on. The next thing would be to integrate this technology with the networking. In fact, one of the recent master's project we had, Antonio Navarro, his master's project was to create basically a shared whiteboard. So 2 people, both having access to a tablet PC, can both open a session and share a whiteboard, and they can interact with each other. So one person draws something, the other person then makes some corrections on it, and so this goes back and forth, and then they can then save the end result. They can create multiple versions, they can save it and reopen it at a future session. You can have multiple users doing these. You can also have one person who has a control, who's like who holds the control over what's being created, as opposed to a distributed setting in which everyone has equal right to do the update. And so a number of different ways in which this idea can be applied. And in fact, this type of project is a very popular one in a number of schools. This type of project work has been going on, and in fact, one of the early projects along these lines was started at Berkeley, and it's still very actively continuing. One other area in which you can use this medium very effectively is dealing with non-Latin alphabets. There are many, many international languages that use very complex representation for fonts. Unicode has been created to alleviate this problem. So basically, Unicode allows us to represent up to 2 to the 16 possible distinct characters. But that doesn't make it easy for someone using a non-Latin alphabet to very easily create input in that language and manipulate it and do editing and so on. Right? So in such cases, of course, everyone, irrespective of how complex the font is, knows to write it, because that's what we learn. When, as soon as you're 1 or 2 years old, you start learning to write, and therefore, no matter how complex the language is, you are very used to writing it with a pen, and therefore it should be possible to use this medium to enter input from those types of languages. And this is definitely the case with my language, for example, where there are close to 200 different characters. And there are keyboards that are available, but they are so complex and so cumbersome that even though I've been using them for years, I'm still finding it very hard. In fact, recently I developed my own application using a tablet PC, which is what now I use for creating my inputs. So I open Windows Journal and I freely write with hand and use my software to convert it into print form, and then I upload it, and it is so much better. So I think these types of applications are becoming very commonplace. And of course, you can think of other innovative ways to use this, for example, new games. So now is a good time to relax a little bit and actually show you one simple game that specifically takes advantage of this tablet PC. So this is a game called Inkball. So when you play this game, so basically your goal is to move these balls. I think I'm at a very low level. I think you will start laughing at me when I play at that level, so I should increase the level. So you can see what's happening is that as it hits these, it changes its color and so on, and your goal is to basically move these balls to their correct position. So for example, blue ball has to end up in this blue slot, so I made a mistake there. As you can see, it entered, and okay. This is a very, very addictive game. But what is really nice about this particular game is that you cannot play this game using a keyboard or mouse. It crucially uses pen as the input. So what is really interesting is coming up with some creative ideas to specifically exploit this pen input to come up with new electronic games. This is in fact one of the areas which we are very much interested in. And one of the first students to work on this, by name Kevin Nishinaga, did a directed study project based on creating a game like this. So now let's talk about in more detail each of these potential applications. Some of it I've already described, so I'll keep moving on. So essentially I'm trying to highlight each of these aspects. So easy to create presentation, how do we integrate figures, text, animation, etc. I think this aspect doesn't require, in fact, too much explanation, but this is a slide that I actually used today in my class. So while you are presenting in the class, you can draw something and then you can immediately save it and post it. So it doesn't require much additional explanation. But what would be helpful in some of these cases is that some of the crudely drawn figures may need to be redrawn more professionally. Right? So I draw a circle, but it doesn't look like a real good circle. I want a perfect circle or a perfect rectangle. So here is actually a very simple tool that originally comes with tablet PC called Windows Journal. It's a very, very rudimentary tool. So what it allows you to do is to open a notebook and it gives you the date and you can write some title and then start scribbling. It's just like a notepad. But it does have a few nice things. So for example, you can say, you can write tablet PC and then you can select it and ask it to actually convert it to text, real print. So it immediately recognizes that what you wrote was tablet PC. So now you can basically save it and do whatever, if you want to convert it, yeah, it does convert it. So it's so convenient. So you can just write it with freehand and then convert it into Word format, and you can now cut and paste into a Word document, etc. Right? But you can also do a little, rudimentary kind of drawing. So, for example, you can go back and select pen and draw that, and then make a selection, and you can say change the shape to circle. So it gives you a perfect circle. So and so on. This one is only capable of giving you straight lines, circles, ellipse, rectangle, and square. That's all this is capable of doing. So even with this, you can do a number of nice things, right? With freehand, you can draw a diagram and use it to clean it up, and then you can export it into some other document and so on. But this is a very, very primitive tool. What we want is something much fancier than this. It's capable of recognizing fairly complex kinds of geometric diagrams, etc. So as we go along, we'll talk a little bit more about some of those things. And in fact, the most recent master's project done in this area is by Steve Bartolini, and his project was the graph recognition. There you can draw a fairly complex graph with nodes, edges, directed edges, nodes, inside nodes, labels, etc. And then it will create this complex diagram, and then it will also allow you to export this in some standard graph formats and so on. Okay. So this, I just wanted to show that this is now becoming a very common place tool. This is a slide I just took from University of Illinois, Urbana, where an introductory computer organization course, the instructor brings the PDF file and then just does the annotation in the class and then reposts. So this is actually taken from one such presentation. So this kind of a technique is now becoming very widely used. So again, we already talked about online discussion, tutoring, etc. So here I just want to mention about this particular tool. I think this Google provides. It's called Scribble, where basically two people can both open this Scribble session and then they can just start exchanging some notes. Right now, imagine if you have access to a tablet PC, the kind of exchange you can do. You can actually draw sketches and write things, and the whole exchange will become far more interesting than if you are stuck with the keyboard and mouse alone. So here are the examples of two non-Latin alphabets. On the left is my native language. On the right you see the language that's the native language of I don't know, Shali's native language is Hindi or not, with Jagans and so on. These are, on the right you see the language that's most widely used Indian language. And these are languages in which the number of different characters is very large. And so the kinds of techniques that are needed for character recognition for these kinds of alphabets is somewhat tricky. And briefly now, let me trace the history of the handwritten recognition problem itself. This is again a problem that has been worked on for more than 50 or 60 years. And the great interest in this problem from an application point of view came from the US Postal Department. For more than 50 years now, they have been interested in building machines that would very, very rapidly read through mail and just looking at the zip code, do the classification. Okay? They don't even want to read the full address and try to do the classification. They just want to sort by zip code, because once that's done, it seems that further classification is relatively easy manually. Okay? So in big post offices, this is what they need. They need a machine that can very, very rapidly do this separation. So into various files based on the zip code. And this is why they put in millions of dollars into various electrical engineering and computer science departments to develop such a tool, and the result, it did pay off. So as of, I think, late 80s or 90s, such machines actually were created and are now in widespread common use in major post offices. But again, even this is a very challenging problem, and remember that you are still only looking at a 5-digit number and trying to do the classification. You can imagine how much harder the problem would be if you had to do a full recognition, because in that case, the challenge will be to, first of all, even to separate various lines. Where does the name end and where does the street name begin and where is the name of the town? Just even separating this whole area into various lines and recognizing one as a name and one as the street name and one as the door number. It's a very, very challenging problem, which is why the Postal Department is happy to just stay with the zip code. Okay. Here are some of the very, very interesting new potential applications. For example, with 3D modeling and artwork. So let's say, for example, you bring up a 3D model of some animal, right? And you want to actually build a 3D model of just, let's say, one of its legs. So what you do is you just trace only the part that you want with a pen. And then, lo and behold, it captures just that part and it gives you, in the mesh, in the standard wire mesh model, the 3D representation of that particular piece. You know, if this type of a thing can be done, it can really revolutionize the way we create 3D models. And I want to actually illustrate this. Once again, a program somewhat similar to this was built by Antonio, but what I'm showing you here is a fancier version of the same program, which was built at Cornell University using a tablet PC. So the way this works is this: with the free pen tip, you draw a 3D object, and then it recognizes the 3D shape and builds the 3D model that you can then save, open, edit, and so on. Okay. So let's actually see what we can do with this. So as a very first step, let's say we want to create a very simple box. Now we can see how we just built the box. See, now it has the full box stove. Right? Now earlier today I was playing with this and I created some models. Let me show you actually one of those. I think Chem4 is an interesting one. I just created this. I wanted to create some kind of a staircase, but of course my dimensions are not quite good, and so I ended up with something. Do you see the stair?
Yeah.
It's just that it's not very well shaped. But I just did this by a very casual free drawing. And it takes, 10 seconds to draw things like this. Now, what they want to do, again, this is a very preliminary stage. What we were able to do was to create a similar tool, except that in our case, all the axes, all these edges, and the facets of the 3D model has to be aligned to X, Y, or Z axis. Whereas this one is more flexible, you can have it in any direction. In fact, you can even have more or less surfaces non-linear. So basically you can have an arbitrary type of surface, which is quite a remarkable thing. So now with this, what they want to be able to do are things like you take two such freehand created the solid models, and then you can move one into the other and perform operations like a union. When you do the union, it fuses them into a new object. When you do intersection, it throws out it retains only the common part of this, and so on. Right? You can imagine the various kinds of fun things that you can do with a tool like this. Right? You can, for example, draw something from one view, and then rotate it from some other view, and then use Snagit to capture that, and that may be the one that you want to post somewhere, or do a number of different things. You can also take a series of these and send it to one standard animation program that will actually create a QuickTime movie that will actually show something in action. So you can think of a number of interesting things that you can do with this. Again, the one that the Cornell has posted is still very rudimentary. It's very primitive at this point. So, moving on, I want to show you some other potential. There's a whole field now coming up called the Non-Photorealistic Rendering, where basically what you want to do is you want to do illustration in which you don't display the photograph, but something that looks like drawn by hand. In fact, Wall Street Journal, all the illustrations are done like that, right? And in fact, I took one such from Wall Street Journal, right? Now I'm going to show you, it took me literally 10 seconds to create the freehand drawing on the right from the one on the left. How did I do that? All you have to do is this. Just take, let me actually try to show you this. Well, I don't have time, maybe, so I won't actually show it now, but believe me, it took me literally 10 seconds to create the drawing on the right. So what you do is you import this into Windows Journal, and then start writing on top of that original picture wherever you feel like. Highlight only the things that you want to highlight. And then just, cut and paste only the strokes that you created in your hand, and that's it. Okay? Now, what is really interesting here is that it is possible to mimic this process and make a computer do this. In other words, what you do is you do a series of such illustrations and let the computer record exactly your eye. In other words, on which parts you focus on. So what it does is it looks at a grid. Depending on the pixel values around that area, it will see, okay, when you see this kind of a contrast, that's where you are putting a pen with such and such pressure. So it keeps a record of all these kinds of actions that you take, and then it now creates your own personality. Then in future, when you give this program just a plain photograph, it will mimic exactly that process and will produce as output a sketch that would look as if you have done it. Okay, yes?
So what it means is it has a learning curve, right?
Yeah, exactly. So this is all the projects that I'm going to talk about all have this flavor of doing what is called data mining and machine learning, and those are the basis for some of the underlying problems that we have to solve. And in this case, what it does is it associates your particular focus area. It looks at the color pixel values around the region where you are particularly focusing on, and uses that idea, and in future when it sees a new photograph that it has never seen before, it does the same mapping. And so it mimics exactly that process. Another interesting problem is creating a mathematics expression recognizer. In fact, this is one of the master's projects that I was going to talk about at some length, but given the speed at which I'm going, I may not be able to get very far. But one master's student actually tackled this problem. So let's say given as input a handwritten expression that looks very complicated like that, with multiple levels of superscript and subscript, with the numerator and denominator, you can imagine all kinds of complexities thrown into it. You can use the sigma notation, integral sign, whatever that you want. So a free-flowing arithmetic expression coming from, say, some advanced math course or something, and you want to be able to create immediately the equivalent version of this. So I want the tablet PC to recognize this and produce the print version like this. Okay. Now a quick interlude now. I'm going to show you how Microsoft actually does exactly something like this. Okay, again, I said, we have exactly a project that was done like this, but our interface doesn't look this fancy, so I'm showing you what actually Microsoft. Let's see, something like this. Okay, so it's pretty good, right? So I just wrote some expression that involved a numerator and a denominator and a square root and a superscript and all that, and it almost instantaneously recognized it and gave me that expression. Right? So now I can cut and paste and say whatever it is. So this is what is called math expression recognizer. And this has now become a fairly well understood problem, but the solutions are still not 100% satisfactory. Probably people achieve close to 95% or so. And
could I ask you a question?
yes.
One problem with the equation editor in Microsoft Word is that you cannot edit it afterwards. It takes it as an image, right?
Well, it depends. I mean, like for example, there is the plugin that comes with the Word, where you can actually select.
Once you enter it, it takes it as an image.
That's right. So what you have to do is, if you want to edit, you have to go back to the original application.
Yes.
That's right. So once you have, let's say you have embedded it in a PowerPoint document, and if you don't have access to the equation editor, then you're really stuck.
Right.
Right.
But then how about this case? I mean, in that application that you had, could you go back to it and modify the equation?
I don't know actually about this, but what we have developed has the ability to go and select any sub-expression directly. So we can actually go back and
Can you take that and put that into, say, Mathematica?
I'm sorry?
Could you put a formula like that into Mathematica and have it graph it?
That's a good question. I haven't tried that.
Or MATLAB or something?
Yeah, that. My guess is probably not.
Okay.
Because I think what you are going to export here would very likely be some kind of a bitmap rather than the actual, some kind of the logical representation of this expression in some form. But even if it allows you to export, I mean, you have to then specifically go under the menu option. Maybe it will say export as, and then might say, in MatCAD or MATLAB or MatMaple or whatever it is, because each one is different. So, okay, what are some of the tools and techniques that are needed to solve these problems? First, I want you to think about one fundamental difference between a traditional version of this problem and the new version of the problem that we are tackling here. Namely, let's say, for example, I mentioned about handwritten recognition as the challenge that the US Postal Department had faced, and it took quite a bit of effort and millions of dollars to solve that problem. Now compare that to same problem, handwritten recognition in the context of tablet PC. There is a fundamental difference between the two problems. The difference is that what you see in the case of recognizing the postal code in a mail is an offline version of the problem, where those digits were written by someone at the background and we don't know exactly how they wrote it. Whereas in the case of a tablet PC, when I'm actually writing it in real time, the computer knows exactly where I started and exactly the various points the pen tip went through in the chronological order. So the temporal information, exactly about the XY coordinates that I touched upon at various times, is available, and that drastically simplifies the problem.
So, for instance, what's the difference between when inputting an O rather than a 0?
Those, of course, are particularly problematic in the sense that you have to have some convention that says that in the case of an O, you have to have some kind of a self-intersection like this, whereas so O doesn't have a self-intersection. So you can always come up with some convention. In other words, see, you're not trying to give a hard time to the computer. You're trying to be cooperative so that it will give you the expected result. Therefore, this is exactly the case where, for example, with the Palm Pilot and PDAs, where A is written like this, with no extra line in between, because there is no other thing that competes with this. So why add that extra complexity by adding that extra stroke and confuse the program? So this is essentially like some kind of a shorthand notation that you agree upon. And this is why in the case of PDF, for example, it requires a training phase during which you give sample inputs, and then it then builds a little knowledge base. It's not a very complex machine learning that it does, but nonetheless, all it's doing is it's making sure that you are following the protocol appropriately, and then it just captures a few idiosyncrasies associated with each specific individual, and then once it's done, then it's ready to go and do a very good job. And the same is the case here as well, in the sense that because of this temporal information available, we can significantly improve the performance. In particular, what we're going to do is we're going to store each stroke in a very compact manner, and therefore comparing two strokes to see whether they represent essentially the same thing or not is a relatively an easy job. Okay, so but I'll highlight this aspect a little bit more. So in the conventional image processing, there are some preliminary steps, things like normalization and thinning and so on. So for example, if someone wrote a letter in a thick font, where the font size is bigger, but you want something that's thin and skeletal like this, so this may be your canonical representation. This one, everyone agrees, is the same as this, except that here the pen tip was chosen to be much thicker than this. But the computer doesn't realize this, because the way the classical image processing algorithms work is they read every one of these pixels one by one. And for them, these two images are radically different from each other, and therefore a very non-trivial preliminary step involves something called thinning. So what you do is you strip all this fat out and then get some kind of a skeletal version of it. And then of course, once you have the skeletal version, you have another problem, namely different writers have a tendency to slant their writing in certain ways, and this can cause another huge problem. Therefore, you have to do some kind of a normalization. You have to rotate it and bring it to some kind of a standard form. All of these take a lot of effort. Whereas in our case, we don't have any of these steps. The way we are going to approach this problem is to view the pen movement as actually creating a stroke. So when you lift the pen and draw a second piece of curve, that becomes a second stroke, and so on. So you collect all these strokes and then you start processing them. Exactly how we process depends on the application that you want to solve. So let me just talk about one particular application, say the map recognizer, and describe in some detail the underlying methodology in tackling this problem. So basically what we want to do, this is what we did. We came up with this very simple idea of creating the so-called signature for each character. And we did this purely in terms of the direction of the movement. Okay. So then what we can do is create a signature. So for example, for each stroke, the signature could be, you know, a string of length n over the alphabet containing just 4 symbols, left, right, up, down, just going in one of the 4 directions, right? So you can just use one of these 4 directions, and then you produce the signature. And of course, this is only the preliminary steps. There are a number of additional things that we have to do. So let's see what are some of the issues involved. But before that, the problem statement is the following. So what we want to do is, given us input some expression like this, I want as output not this. We didn't end up creating this kind of actual nicely typeset output, but rather a language in which exactly this expression is described, a language called LaTeX or TeX, in which basically what it does is it allows you to describe this by specifying exactly how things are grouped. So for example, the word over here means that this is the numerator and this is the denominator and so on. So there is further another fraction there. So this represents Q over A plus B, and you use braces to show which are aligned, etc. So in fact, if you take this and run this through a particular program called the LaTeX program, then it will produce a PostScript file that contains this. Okay, so this is there is some advantage in doing this, because scientists and engineers who write technical documents all the time prepare the documents in this language using this thing called the LaTeX or TeX. And for them, it will be very convenient if it can give an output that they can then cut and paste into their document. For them, this is not particularly helpful because they cannot easily integrate this into a document that they already have. So this is the slight difference in the way we pursued this problem. So there are a few tricky issues, particularly related to the two-dimensional nature of the inputs, and there are also some somewhat tricky parsing problems or reading and understanding the expression that is unique for mathematical expression. So for example, something like a power b plus c is okay, but a subscript b plus c is not okay. So it uses this knowledge. So for example, when it sees a subscript b plus c, it will guess that very likely this plus c has to be aligned with a. Okay, of course it has other information. So the way it actually works is it uses the concept called a bounding box. It bounds each character by a box. It encloses it in a tight box, and then looks at the middle of the box, and the position of the middle of that box determines which is aligned to what. Okay, but there has to be some room for error, because after all, you are doing all this by freehand. In fact, we are doing this on a tablet screen that is not even ruled. It is plain, and therefore you might have some misalignment and so on. So the overall layout of our technique goes as follows. So you have the initial drawing that's read by a particular module called feature extractor, which then produces a signature. The signature is nothing but the string of L, U, L, R, U, and D, left, right, up, down. And then we have something called the stroke descriptions. So basically, all the stroke descriptions associated with all the standard characters, individual letters. So for example, alpha, A, sigma, opening bracket. Each one has a standard stroked representation associated with it, and you are doing a pattern matching with that to recognize the various strokes. Then what you do is you do various stroke combinations. In fact, even this part, there are lots of steps involved. So for example, basically what we have is, we have, this classifier is something called a decision list. Okay. So a decision list is something that, in fact, the easiest way to relate to something in real world is, say for example, suppose you want to know whether tomorrow is going to be cloudy or not. You want to capture whether tomorrow's weather in terms of some simple sets of rules. Say for example, if the temperature in the morning was 45 degrees and it was cloudy the previous day, or if it was cold the previous day. So if you have a set of rules like this, then you can say that tomorrow is going to be also cold. So you come up with a series of such rules, and this collection is called a decision list. And in fact, decision lists of this kind are, for example, used in things like determining the mortgage rate, or whether one's credit rate is considered good, excellent, or whether someone qualifies for something. These things can be captured in terms of a set of rules like this. And so that's what we actually use. So we take all the information about various ways of writing different characters and collect all that information and then send it to an algorithm which will then come up with a set of a sequence of decision rules called decision list, which is what is actually used for processing in that step. And then from there we move on to the symbol recognition. So for example, many of the symbols in math, I know we have only, I think I have to speed up. So from there we combine the various strokes into symbols, and then we have to recognize the spatial relationship to realize, for example, the various sub-expressions. Specifically, the real challenge comes in separating the numerator and denominator. If you have multiple quotient kind of expressions, exactly identifying where the various sub-expressions are. And so that's basically how this whole thing goes. And I just want to give you some examples to show how this stroke signature is created and how that itself is incomplete information. So for example, when you write a G like this, the signature would come out to be something like L. You start going left initially, right? And then you go down, and then you turn right, and then you go up, and so on, right? So the signature will be something like LDRUDL, but the same letter, when you go further, then the signature becomes different. Therefore, we need to keep track of all the possible signatures associated with every reasonable way of writing that letter. To make matters worse, you can have the same signature, but that can correspond to different characters. So you have the false positive as well as the false negative situation here. So for example, if you look at LDRUD, if you use exactly this signature to write this, it'll be an A. If you do exactly the same thing to write that, it'll be D, and so on. So, they all look somewhat similar to each other, and therefore, just the signature alone is not enough. So you need to have additional coordinate information. So you have to say, for example, the XY coordinates of the uppermost point relative to the various inflection points where things, directions drastically change. You have to say something about the relative orientation of the X or Y values of both. Okay, so we have to collect all this information, and we have to then make some kind of a decision process based on this. That cannot be done manually. That's the crucial thing. So we need an algorithm to mechanically do this, and this is exactly what these machine learning algorithms do. Once you have all this data available, then you can send this to this algorithm, which can then give you back what is called a decision list or a decision tree, which can then be used to do the processing. Okay. So I think, given that I have literally 5 more minutes left, let me move on and talk about really the, so I have, for example, one of the master's thesis was written based for Japanese character recognition. Kevin Nishinaga happens to have Japanese as his native language, so he actually came up with, so he used the decision tree model, but to create the decision tree, you needed a neural network and so on. Again, I won't go into all the details. Here are some results. So he was able to go up to, for most of the characters, he was able to get 95, 90 to 95%, but occasionally there are some characters that didn't do particularly well. So the, moving on, what are some of the interesting problems that we face at this point? What are some of the directions in which we can work further? For example, one thing that we are really interested in is the following. We want to create a single integrated framework that is capable of integrating the various recognizers and act as a single tool. What do I mean by that? So you saw Windows Journal, right? This is what is the raw notebook that comes with the tablet PC. And I showed you its functionality. It's very rudimentary, it's workable. I mean, it's a notebook where you can do free writing, and you can do some character recognition, you can draw some very primitive shapes, like circles and so on, right? And that's about it. But what we want is take it to a completely new level by building various recognizers into it. So for example, on the same notebook like this, I want to be able to do some drawing that then gets recognized as the corresponding 3D shape. I may want to draw an electrical circuit, or I may want to do some writing in a non-Latin alphabet, or I want to write math expression. All of this, it recognizes. Okay. The framework that we were proposing to do this is as follows. So we'll have basically each of these plugin that works. But then when you actually create a stroke, what happens is that that stroke gets passed to all these recognizers, and each one says how confident that recognizer is in recognizing what it is sensing. And then the best of those will be given the job of actually interpreting it. So basically, so by delegating it to each one of these recognizers, we get, while you are moving from expression to some drawing, then the drawing program says, oh, now I know what it is. It looks like a circle. Whereas at that point, the math recognizer is lost. It doesn't know what it is, and so on. So by being able to engage each of these recognizers separately, we then want to recognize this whole document, and then we can convert this entire document in a nicely typeset form, or whatever that we want to do. We may want to save each separate piece in one separate file, etc. Right? So that's the kind of framework that we want to create. But in fact, we do even have a rudimentary version of this framework, but work still has to be done. But before I stop, I just want to show one fun program that is already that has been created. Again, this one is Microsoft product, and it's really a neat one. And then I'll continue with one more slide and then really conclude. The way it works is, this is what is called physics simulator. And so you can set up a physical system, classical physics system, basically balls and obstacles, inclined plane and so on. And then you also specify certain forces. You can say, I want the force to be applied in this particular direction. And then the whole physical system exactly mimics the way in a real world, if you had set up all those things, a ball and an inclined plane and a box interrupting this flow, all those things where we need to simulate. But what is really neat about this is the tablet PC becomes a lot more fun, because you can now draw these things with a free hand, and creating these scenarios becomes much more interesting. So let me first show you the way it currently works. This is something that was created initially. So you see, that's the force direction that you have specified, and you can see how it's just okay. So now let's do the same. Let me just open the same thing. No, it's and then let me just add a ball here. Another ball. Right. And then let's see what it does.
ball has some mass to it.
Maybe eventually, in some cases, artists go really surprised. Of course, friction, all the parameters are there. You can specify its, elasticity and coefficient of restitution, all the various physical parameters that you want. But, do you really believe that, how trustworthy it is? That's a completely different question. For example, these days in tennis, for example, there is the action replay where they actually have a simulation that shows whether the ball landed, exactly at which position on the line. Everyone religiously, completely believes in that simulation, and nobody even questions. Even McEnroe, if he sees that, wouldn't object, he'll just walk out accepting it. So this is a new high-tech way of, cheating, whatever it is, but it's quite interesting. But what is really nice about this is that with the pen, it makes it a lot easier to create these inputs. Maybe I should just change the size of the ball a little bit, and then don't want to take away the pleasure of actually seeing this fall away. So let's hope that this will take that job. So. Okay. So. The same way I already mentioned that there is this, there's a tremendous opportunity to integrate this with artwork, especially 3D modeling and stuff like that. On those issues, currently we are in very, very early stage. When I say we, I mean in the whole world. I mean, even the state of the art is still in very, very primitive level, and so the opportunities are quite enormous. So in conclusion, when Tablet PC came along, people really thought that it'll really take over, but that hasn't happened, right? But I think it's very slowly making inroads and making progress. The real problem at this point, there are a number of issues. One is clearly the additional price that people are not willing to do it. But more importantly, the paradigm shift. Not everyone is prepared to do that extra learning that needs to be done in order to make it into a convenient tool. But most importantly, we don't yet have a killer app, something that will just dramatically change. I mean, people, once they see something like that, they'll say, okay, this is it. From now on, I'm not going back to my old machine. I want this. There is no such application as yet. But who knows? I think that's all I wanted to say.
Question. First of all, would you be able to do any